In this video, we're going to look at the row vibrational analysis of the carbon monoxide and carbon dioxide product gases from our combustion experiment. We'll start by taking a look at the spectrum of a simple diatomic molecule and how we analyze that to get information about rotational constants and ultimately about the bond length for the diatomic. In this case, of course, carbon monoxide is our diatomic, but we're going to look at the HCl spectrum, which is one that we've discussed earlier. So in this spectrum, we can see at the bottom of our page here the spectrum of HCl. So here we have the IR spectrum of HCl corresponding to an n equals 0 to 1 vibrational transition, accompanied by a series of lines corresponding to rotational transitions. And of course, you'll recognize this from our past discussions, that on the high frequency side of the center gap, we have the R branch, where the R branch corresponds to delta J equal to plus 1. So we would have, for example, here on this peak, we have a delta J plus 1 transition where it's going from J equals 0 in the lower vibrational level to J equal 1 in the upper vibrational level. And then, of course, we go from 1 to 2, 2 to 3, etc. On the R branch side. On the other side, on the low frequency side, we have the P branch, which, of course, corresponds to delta J equal to minus 1 transitions, so that the first peak here corresponds to a J equal 1 rotational level in the lower vibrational state to a J equals 0 level in the upper vibrational state. Now, of course, this is shown in this upper diagram here, which shows the rotational energy levels in n equals 0 and the rotational levels in n equal to 1. So all the transitions in this IR spectrum are going from the situation of vibrational level 0 down here at the bottom to vibrational level 1, and then the red arrows show the corresponding rotational transitions. So we get this series of peaks in the spectrum. Of course, when we look closely at this spectrum, we'll notice that the spacing here between lines looks to be roughly the same for all of them. And if you recall from our earlier discussions, that spacing was equal to 2 times the rotational constant. And we could use that estimate of 2b for the spacing to calculate the rotational constant b, the moment of inertia, and therefore the bond length. Of course, as you know, that what we tend to learn on our first attempt is just an approximation. As we'll see in the spectra that we get from the IR, that spacing is not constant, and we'll talk about why that is briefly in a few seconds. Before we talk about that, however, we just need to look at some basic equations here corresponding to the energy of a system as a function of quantum numbers n and j. N, again, of course, represents the vibrational quantum number, and j represents our rotational quantum number in this situation. So in this expression, and again, all of these are in terms of wave numbers represented by, of course, the little squiggly line on top here. So we are talking wave numbers and not joules in this discussion. So the first two terms in our equation here correspond to vibrational energy associated with the n quantum number. We have nu e, what we refer to as the equilibrium frequency, and nu e xe, where xe corresponds to anharmonicity in this situation, as we discussed earlier, and xe, of course, is the anharmonicity constant. The last term in our equation corresponds to rotational energy for quantum number J. And what we're going to note here is something that we haven't discussed before, and that is that the rotational constant, which you'll note has a subscript n here, actually depends on the n quantum number. And that's simply because the original equations derived for rotational energy were based on an assumption that we had a rigid rotor, meaning that the distance between the nuclei remained constant throughout the rotation. Of course, this is not true. The nuclei are vibrating, and because they're vibrating, their distance is changing throughout the rotation, which also means that the moment of inertia changes throughout the rotation. So the degree to which the moment of inertia changes depends on the quantum number n. The higher the quantum number n, the greater the change in the moment of inertia through a vibration, because the vibrational amplitude is greater. And so that means we need to add the correctional factor here, which is shown in this equation. So B sub n depends on the quantum number n, and then we have BE, the equilibrium rotational constant, and then we have the second term, which accounts for rotation vibration coupling. And in fact, the alpha E is referred to as the rotational vibrational coupling constant because it does relate. It shows how the rotational constant depends on the quantum number n. All right. So again, you'll notice that the higher the quantum number n, the greater the quantity that's subtracted from B sub E. So again, what we're going to be determining in this experiment is B sub E, and from B sub E we can get the moment of inertia, and of course from the moment of inertia we can get the bond length. Now, without going through all of the nitty-gritty of the derivation of the transition equations, we'll just simply lay the basic expressions out here. So when we have an R branch transition where we're going from n to n plus 1, which in this case corresponds to 0 to 1 for the vibrations, the R branch means we're going from a J value to J plus 1. All right, so we're increasing our J quantum number by 1 in the R branch. The double prime here is actually just simply used to indicate that it's the rotational quantum number corresponding to the lower vibrational state. This is just normal spectroscopy speak. So the double prime means that we're going from J double prime in the lower energy state to J double prime plus 1 in the upper vibrational state. And then we end up with our equation here that shows us the relationship of our transition. So nu sub r would be what we measure in the laboratory, wave number wise, and that can be related to this assemblage of coefficients. It is important to note that nu sub 0, you won't see the anharmonicity x sub e in this equation because we won't have enough data to determine that. So nu sub 0 is actually just very simply equal to nu sub e minus nu sub e xe times 2. Okay, so that's what nu sub 0 is equal to. And that would be dead center in the middle of our spectrum. So this would correspond right here in the middle of our spectrum to nu sub e. Nu sub 0. And again, we're not going to be determining the anharmonicity constant from our data here. So that's our R branch data. And so we can see that it's a quadratic function of the rotational constant J double prime. So we can take our IR spectra and we can assign the peaks to the different J double prime quantum numbers, and from those quantum numbers we can do a quadratic fit to determine all of the parameters in this equation. We can look at the P branch in the same way. In the P branch, of course, the only difference is we're going from J double prime to J double prime minus 1, so the equation looks a little bit simpler And again, we'll note that it's quadratic with respect to J double prime. So again, taking our data, our wave numbers from our IR spectrum and plotting it versus J double prime will allow us to extract parameters. So one could actually do two separate plots, one of the R branch and fit it to this equation, one of the P branch and fit it to this equation, get the coefficients so we can see that we can get from both of these equations B sub B, alpha E, and nu 0 from both equations, and we could just average them. But it turns out there's an even better way to do this, and we can combine the R branch and the P branch by actually defining a new number here. And our new number is M, which is defined for the R branch as J double prime plus 1, and for the P branch is defined as negative J double prime. And when we do that, we actually end up with one single equation. So this will allow us to combine the R branch and the P branch data and plot it versus this new number M, and to extract the data nu 0, rotational constant B sub B, and alpha E. So let's just look real quickly at how we'll go about doing this in terms of assigning the M values. And once we assign the M values, we can do this quadratic fit. So what we have here is some sample data from HCl. We have the R branch, and you can see if you were to actually look at this and draw it, these are the data that we would get from the peaks that we saw earlier. So for the R branch, we have this peak here, 2905, which corresponds to the 0 to 1 transition. So one of the things that we're going to need to do, of course, when you gather your data, and we'll talk about this when you actually have data, is to assign the different J values to your data. But in any event, this is going to be the R branch. And so again, just using the simple rule that we had before, when we have the R branch, we define this M quantum number as being J double prime plus 1. So I'm just going to enter the equation equals J double prime plus 1 for our R branch data. And I'm just going to copy that down for the R branch data. Let's try that again. Okay, so there's our R branch data, and we can see we have the graph here. And then I'll do the same thing for our P branch data where it's negative J. And so for a P branch data, I'm going to do equals negative, and then I'm going to copy that down like so. And so now I've got my R branch and my P branch data on the same graph. Okay, and now what I'm going to do is I want to do a quadratic fit to this, and I want uncertainties in my results, so I'm not going to do a trend line analysis. I'm going to do the quadratic fitting analysis that we discussed earlier in the semester. I'm not going to demonstrate that here for you, but we did discuss it earlier in the semester, and we went through some examples of that early in the semester. Okay, so now let's take a look at carbon dioxide, because the equations are going to be slightly different. Carbon dioxide being a linear triatomic, not a diatomic, we have slightly different expressions. Carbon dioxide, of course, has 4 vibrational modes: the symmetric stretch, the anti-symmetric stretch, and 2 bending modes. We're going to be focusing on the anti-symmetric stretch in our analysis here. So this is an example spectrum of the carbon dioxide anti-symmetric stretch. The high frequency end, of course, over here corresponding to our R branch, delta J equal to plus 1. The low frequency side is the P branch with delta J equal minus 1. If we take a look at the equations corresponding to the carbon dioxide situation, there are a couple of differences as noted earlier. We can still define the quantum number M in the same way as we had before, so we can combine the P and the R branches, but we have a slight difference here. So for one, we refer to the rotational constant B0 because the rotational constant includes all of the vibrational modes of the molecule. So we define things a little bit differently. It's only the antisymmetric stretch that is being excited. The other modes are not being excited in this transition. So we do have a slight difference. But the idea is the same. We're going to take our data from the IR, we're going to plot it versus our quantum number m and do a quadratic fit to get the vibration rotation coupling constant, alpha sub 3 here, which actually means it's the vibration rotation coupling constant for the antisymmetric stretch. It is different for the different vibrational modes. We'll get what's referred to as nu3, which corresponds to that 0 frequency for the antisymmetric stretch, and of course our rotational constant b when we do this. Once we get the rotational constant b, of course we can once again calculate the moment of inertia, but to calculate the bond length we have to be careful because the expression is different. And because the expression is different, that means that we have to look it up. I'm not going to give it to you, but you need to find the expression for the moment of inertia of carbon dioxide in order to calculate the bond length. The other thing that's important to note is that because of the Pauli principle, and you'll remember the Pauli principle as requiring that our wave functions be antisymmetric with respect to exchange of fermions or electrons, because they are fermions. They also require, it also has an impact on symmetric molecules like CO2, which has a carbon with oxygen 16 on either side of it, and oxygen 16 has a spin quantum number of 0, and that means it is a boson, and the wave function has to be symmetric with respect to exchange of bosons. Now the net result of that is that for the n equals 0 vibrational level, only the even J levels are allowed. That means that molecules cannot exist in J double prime equal 1, for example, when the vibrational quantum number is equal to 0. So that actually means that half of the vibrational lines that, rotational lines that we would have seen in carbon monoxide, where all are allowed, are not present in carbon dioxide. So if we go back and take a look at the spectrum for carbon dioxide, we'll see how that occurs, how that has an impact on how we assign our lines. Okay, so for example, if we look at this spectrum, what we're going to see is that, so here is our central peak here. When we look at the spectrum, on the low frequency side, the first one's going to correspond to our is going to correspond to our P branch. And for the P branch, what we're going to note is that because J double prime equals 1 cannot exist, the first one is a 2-to-1 transition. All right, so J double prime equals 2 is that first peak on that side. Okay, it's not J double prime equal to 1, which is what it is for carbon monoxide. On the R branch side, the first peak in carbon monoxide was a 0-to-1 transition, and here we also have a 0-to-1 transition because J double prime equals 0 is allowed. The second peak, however, which in carbon monoxide would be a 1-to-2 transition, well, because J double prime equals 1 cannot exist, then we have skipped that, and this becomes a J double prime equals 2-to-3 transition. All right, and then J double prime equals 3 can't work, so the next one is J double prime 4-to-5 transition. So you have to be careful with the assignments here for carbon dioxide, because it's going to go on the R branch side 0, 2, 4, 6, 8. Okay, and on the P branch side, it's going to go 2, 4, 6, 8, etc. as well. So be careful about that when you're creating your spreadsheet and assigning your J values to the transitions. So again, what you're going to be doing here is after you've assigned those transitions carefully for carbon dioxide and you've calculated the M values as we talked about earlier, you're going to be plotting nu versus M and doing a quadratic fit, not a trend line analysis, doing a quadratic fit to determine those parameters, alpha, B sub 0, nu sub 3, and again from the B sub 0 you should be able to calculate the bond length. Certainly if you have any questions, feel free to ask. Otherwise, we're finished with our discussion here.